Hi, my name is Justin Minder. I'm going to be speaking to you today about an overview of scientific field campaigns and kind of the process that we go through to plan, execute, and manage the data that comes from these field campaigns. I'm an associate professor here at the University at Albany, and I participated in a number of field campaigns over the years. I'm an atmospheric scientist by training, and a lot of my field research is focused on winter precipitation, from rainstorms over mountains to lake effect snowstorms, to big winter storms. And in my talk today, I'm going to show you some examples throughout the talk from a recent field campaign that I just led called Wintry Mix, which you see the logo of here, and I'll describe it more as we go along. So I tried to think through what are the major components, that major pieces you need to put together to have a successful field campaign, and I've kind of put them here in these little boxes. I've intentionally not put them in a clear order because they don't necessarily all happen in order, but generally with the colors, there's the things you do on the top before the actual field observations. There's the things you do in the field, which I put all here under field operations. And then there's the things you tend to do after the observations have been collected, which are down here on the bottom. So the structure of this lecture is I'm going to go through each of these in turn, talk about them in general, but then also give you some specific examples from this field campaign that my group just participated in. So first, just a little bit of background on my field campaign. It's called Wintry Mix, the Winter Precipitation Type Research Multi-Scale Experiment, and it took place in early 2022, so it's about a year ago. And the focus of this project, you see here the kind of mission statement: to better understand how multi-scale processes influence the variability and predictability of precipitation type and amount under near freezing surface conditions. So what we're interested in is, the processes that lead you to get these different types of winter precipitation, especially when the temperature is right near the freezing threshold. Are you going to get snow, so just ice crystals falling out of the sky? Are you going to get rain, snow that melts into liquid water? Or are you going to get one of these transitional precipitation types like sleet, where the snow melts, but then becomes supercooled after melting? That water becomes supercooled and refreezes before it hits the surface, or freezing rain, where the refreezing happens on the surface. The details you don't need to worry about, but this is the big picture of this project. And we're looking at it from all different aspects, all the way down from the small scale physics of the individual precipitation particles up to the big, large scale storms that are responsible for the precipitation. Okay, so the first thing you need to do generally before you execute or even plan your field project is you need to decide what you're going to focus on. You need to kind of conceive of the idea and the focus of your project. And so I've listed a few things you might want to consider as you're going through that process. One thing is, what are the gaps in our understanding of the atmosphere? We're talking about atmospheric science field campaigns here. So what's something we still don't understand about the atmosphere that we'd like to understand better? Also, what are observational tools and techniques that are available to study this phenomena in the field? How can we characterize different aspects of whatever it is that we're trying to understand? Also, what are the impacts of different weather and climate phenomena on society? A lot of these major field campaigns they're quite expensive. So if your focus is on studying some kind of very local phenomena, or maybe a phenomena that doesn't have much societal impact, it might be much harder to get funding for that than if you're trying to study, something like a tropical cyclone intensification, where there's very clear societal impacts to such a process. And you also might want to think about how or when was the phenomena you're interested in last studied. You need to generally make a case that whatever project you're proposing is going to yield some new information, and it's going to be worth the investment. Well, if it's been studied recently, you need to make the case of how what you're going to do in your field project is going to add something novel, or you're going to have a very hard time getting people to want to fund it. So some things that are useful to have in the focus of your project. One is to have a strong and clear motivation. Why are you studying? Why do you want to study the thing that you want to study? You know, that can relate to the societal impacts, that can relate to fundamental gaps in our scientific knowledge, but you should have a clear, specific reasoning there. It's also very important and valuable to have specific testable hypotheses. So you want to not just say, I want to study tornadoes. You want to have a specific hypothesis about some aspect of, you know, why tornadoes form where they do, and put forth a specific idea that can then be tested with observations and proven, potentially proven wrong, because that's how science works. We want to have testable hypotheses. Without that, you might lack the focus to put together a successful field project. It's also important to have novel tools, questions, or approaches. Again, you don't want to just be rehashing the same science that people have done in the past, and have a high likelihood of success. You want to make sure that if you're proposing to go out and say, study a certain weather phenomena, that you have high confidence that it's going to happen, and it's going to happen frequently enough that you can get the sample size you need to draw firm conclusions. Just a general point is, you know, read the literature. It's really important to look back extensively at what other people have done in the past in the area that you want to study. Also, what questions have others posed? That often at the end of a scientific article, people will state kind of existing or remaining scientific questions that haven't been answered about the topic they've written about. Often that's a good place to look for ideas. Okay, how might you be able to use observations in the field to answer some of those questions? Sometimes there's results that come out of a modeling study that are very intriguing, but don't have yet observational support. That can sometimes be one way to come up with a good idea for a field campaign, something that's found in a model, but people haven't really been able to support with observations yet. You can try to go and find those observations. Often you might want to think about this framework of, are you using new or old tools, or asking new or old questions? Often you want to combine one of those news with one of those olds. If you have a new tool, you might be able to find better answers to old questions than people have found before. Say there's some new radar technology that you can all of a sudden answer a question that people weren't able to answer previously. Or you might have an old tool, but a novel question. So you might be able to use a proven observational tool to answer a question that's kind of new and creative. That's another winning combination potentially. So let's give you some examples from Wintry Mix, the campaign that we just did. These are, I'm showing you some quotes here from the proposal where we proposed this project for funding, to highlight how we approach some of these aspects of identifying our focus. So one thing was we tried to identify gaps in understanding. We used this this quote from a research report saying that the most serious problem with wintertime quantitative precipitation forecasting is the accurate determination of precipitation type. So that's a statement. It's kind of saying that there's a problem there that we can potentially address. Also, you want to think, like you said, of when was the phenomenon last studied? Well, we made this case that no major recent campaign has focused on near freezing surface precipitation, kind of making this case that the time was ripe for us to do the observations that we wanted to do. We also mentioned the importance of impacts on weather and climate and society. So in our proposal, we mentioned this historical and very damaging ice storm that happened in the same region that we wanted to study. In 1998, this big ice storm, which caused numerous deaths, power outages, billions of dollars in damages, and huge impacts on the local forests. So this is one of the ways that we motivated the observations that we wanted to collect. Also, we talked about novel questions, tools, and approaches. Well, we listed some of the things that we thought were novel tools that we could leverage in this. For instance, recent advances in numerical modeling and dual polarization radar technology that we would be able to use to understand these storms better than previous researchers had. And then finally, these specific testable hypotheses and novel questions in our proposal, we listed out some kind of broad scientific questions you see in the bold here. For instance, how do mesoscale dynamics modulate near freezing precipitation? But then we, underneath them, listed out, I'm just showing you a few of them, very specific and testable hypotheses, such as this one, that terrain channeled advection and terrain trapping of cold air determine the persistence and depth of near surface subfreezing valley air. And erosion of that cold air can lead to abrupt changes in precipitation type. So a much more detailed hypothesis that we can potentially test and prove wrong, or find support for with our observations. Okay, so that's how we might kind of come up with an initial idea for what you want to study. But then you need to start planning out the details, the who, the what, the where, the when of your field campaign. So in terms of the who, one important question to ask is who should be on the research team, especially for larger campaigns. You need to bring a lot of people together to make them happen. This includes principal investigators, so these would be the research group leaders in the project, and also people that work under them, such as research scientists, instrument engineers, graduate or undergraduate students, program managers, forecasters. These can all be important members of the team. Your team needs to have adequate expertise in the phenomenon being studied. So, we're studying winter storms, so we need to have people that have some expertise in that. But also the instruments and techniques that are going to be used to study those, be that radar, radio sound observations, aircraft observations, whatever they may be. Some things to consider when you're thinking about who should be on your team. Who has access to what instruments? So certain research groups own their own instruments that they can then bring with them into the field, or access to certain research facilities, or access to certain funding streams. That can be important practically to make a field project happen. But you also need to find people that can work together as a team. If you have people that are going to be, not able to be very collaborative and are going to kind of start feuds and make things difficult, then that might be hard to pull them together and have an effective project. But if you have people that are good at being collaborative, that can really increase your chances for success. And also you want to think about having diversity of backgrounds, people that come from different demographic groups, different backgrounds, can be important for giving different perspectives, but also scientific backgrounds can give you different approaches to the problems you're studying. So again, some examples from Wintry Mix. Well, here's our team of principal investigators. You see, they came from many different institutions and have many different expertises. So I was the overall lead of the project, but we've got folks like Fred Fabry here and Dave Kingsmill who have a lot of expertise, as well as Kwong Nguyen here, who have expertise in radar meteorology, folks with expertise in aircraft observations like Leonid, Mengistu, Kwong, and Jeff here. Also should have mentioned Katja in terms of radar meteorology. Expertise in synoptic meteorology like John and Andrew here, or microphysical processes like Julie and Jeff, or forecasting applications like Nick Basil here. Also forgot to mention Karen with respect to radar expertise. And so these people are coming from all different institutions and coming together to make this happen. But these were just the leaders of the different research groups. We had many other people who participated, including dozens of students, both undergraduate students and graduate students, as well as at least one postdoctoral scholar, research scientists, engineers associated with the radars and the aircraft, technicians, pilots for the aircraft, forecasters, and even people that were managing our data sets and websites, including folks at the Earth Observing Laboratory of NCAR. Okay, so that's the who. So what about the where and the when? So where should your project be? Things to consider here are, what's the climatology of your phenomena of interest? If you want to go out and study a certain type of phenomena, such as say freezing rain, you want to make sure that you're going somewhere where it happens frequently enough that you can be confident that you're going to be able to observe that thing. You also want to think about, can you find a region that has pre-existing facilities to leverage? For instance, operational weather observations that are already there that you can build on, instead of having to bring all your observations yourself. And also you want to think about logistical challenges. So, maybe you could observe the same weather phenomena in two different places, say, in a developed part of the US or a remote and hard to access part of South America. If you can equally address the research questions in those two places, you might want to favor the place that is easier to get to and has better infrastructure to get around and to site your instruments, rather than making it harder and more expensive than it has to be. Of course, there's other situations where maybe you need to go to the remote place that's hard and challenging to work in, because that's where you need to go to see what you want to see. But that's something to at least consider. You also want to consider, when should your observations be collected? Again, you want to think of the climatology of your phenomena of interest. What time of year, what season is this most likely to occur, whatever it is that you're trying to study. How long you're going to need to take observations for. What's a sufficient length of time to go into the field that you can have confidence that you'll be able to observe the phenomena you need to observe, and that you can observe it a sufficient number of times to collect good data. And again, thinking about logistical challenges, if you go to certain places in certain times of the year, there might be a lightning hazard that makes it difficult for you to operate your instruments, for instance, or heavy snowstorms that make it hard to get to your field sites. And so you need to take those into account as well. And through all this, you need to consider resource limitations. Maybe ideally you'd like to do your field project over some huge geographic area and spanning 3 years, but unfortunately, we often can't do all those things that we want to do because there's financial limitations or staffing limitations that constrain how long we can be in the field and how far and how remote of a location we can travel to. So that needs to be factored into this where and this when as well. So let's give us some examples of what we decided for wintry mix. The where, we focused on this kind of border region between the US and Canada, in kind of northern New York, and mostly northern New York and southern Quebec. And mostly focused on this Lake Champlain Valley and the St. Lawrence Valley that you see in this topographic map here. One reason we chose this region is because there was a really excellent backbone of existing observations. There's two advanced surface mesonet networks of atmospheric observations in New York, which is these NYSM, New York State Mesonet dots, and up in Canada, these CFI Climate Sentinel dots. These are advanced weather stations that we're already going to be able to get data to, that we could then add additional sensors to the region to elaborate on the data. There's also good coverage from operational weather radars, both in the US here, where this S is, and in Canada up here. So these were favorable things for this region. It's also a region that receives plentiful near freezing winter precipitation. We looked at some climatologies of how often near freezing precipitation occurs and how often freezing rain occurs, and those demonstrate that the type of weather we wanted to observe occurs frequently in this region. And there's also interesting terrain effects on the weather. These valleys that you see here have interesting influences on the precipitation type that we wanted to study, so that favored this region as well. When we focused on February to mid-March of this past year, this is from our climatology, we had an expectation of about 15 days would occur in that period of near freezing precipitation, so it was a favorable time period for us from that respect as well. So for one of the big what's you need to answer is, what observations or instruments do you need to address your scientific questions or hypotheses that you identified? And you can consider a whole host of different types of instruments, anything from surface stations to balloon-borne instruments, to aircraft, to shipborne instruments, buoys, and radars, and all different things. But as you're thinking about what you want to be part of your observation network, you need to ask yourself a whole host of questions. How expensive are these different instruments to deploy? Ideally, many of us would probably love to go out and put out everything you see in this picture, but that's not practical. How reliable are these instruments? Some instruments can be very finicky. Maybe they're based on new technology that's that only works sometimes. So you want to make sure that you don't hinge your whole project on a observation that only has a 50% chance of working. What's the coverage of your instrumentation in space and time? So you want to make sure that that's well matched to the space and time scales of the phenomenon you're trying to study. I also want to think about what novel information will be provided. By bringing out these instruments, which things are going to be able to really yield new insights into the thing you're trying to study. But you also want to think about not just the observations in isolation, but by combining data from different instruments, different measurement platforms, how can you bring them together to make them more than a sum of their parts? But again, with all this, we need to consider resource limitations. What's the availability of the instruments you want? How much money is required? What's the staffing required, and so on. So to go into what we decided for Wintry Mix, there was two really major instrument facilities that we used in this project. One was a research aircraft called the NRC Convair 580. And this has a whole host of different instrumentation on it. You see a picture of inside the cabin and all these things mounted on the wings and the fuselage of the aircraft. They include measurements of the thermodynamics of the atmosphere and the wind as the aircraft flies through, as well as probes along the wings that measure cloud particles and precipitation particles and aerosols as the aircraft flies through the atmosphere. Also on the side of the aircraft, there's a profiling radar that measures radar variables in the W and X bands, and a LiDAR that is able to characterize things like aerosol profiles. Very important for us is this aircraft was capable of operating in supercooled clouds and icing conditions, which were the type of conditions we wanted to study in our project. And we, in this project, we had 9 research flights, each of about 4 hours each. So we had to consider how long the aircraft could be in the air, roughly 4 hours on a mission. And that put some constraints on where we can fly it and what we can observe. Then we also had these mobile Doppler radars. We actually had 3 of them, 2 that looked like this. These are X-band scanning radars with dual polarization. They're great for mapping out precipitation and how it's varying in space and time, as well as in type. They also help you to map out the winds using their Doppler capabilities. And then there's a larger C-band radar that we also deployed, which has a bit of a different wavelength and a wider range of measurement. But then those weren't the only assets that we had. We also had our really important manual observation teams. And these were, you'll see, deployed throughout our region from 4 different universities. And they were really great. They were led by students and a postdoc for each of these teams. They launched around 200 radiosondes during the project to give us vertical profiles through these storms. And they also collected manual precipitation observations at the surface, which were really important as well. And then also, in addition to the existing weather stations that were in the region, we had some specially deployed ground-based instruments where we either added to existing weather stations, or in the case of the one you see pictured here, basically installed an entire temporary advanced weather station just for our field project. So kind of pulling together some of the things we've talked about already, we have these different instruments and measurement platforms, and then we have these different questions and hypotheses. And one thing you want to do is you want to make sure that they're well matched, that you're using the right observations, that they're well suited to answer the questions, to address the hypotheses that you have. And so this was a table that we had in our research proposal where we're in the columns, you're seeing these different questions that we posed, as well as the specific hypotheses, H1.1, H1.2, and so on, from our proposal. And then as you go down through the rows, you're seeing some of the different instrumentation that we were proposing to deploy, and with 1 or 2 check marks, we're showing how vital they were to answering each of the questions, addressing each of the hypotheses that we had in the project. And so this kind of matrix is a useful way maybe to kind of make sure that you're covering your bases and you have the adequate data, to address your hypotheses, but also that you're not putting out instruments, expensive instruments that don't serve to really add to addressing your questions and hypotheses. Okay, so then there's also some how questions you might need to ask. For instance, how will your instruments be deployed and operated to address your research goals? When you're putting out your instruments and operating them, how are they going to be able to resolve the scale of your phenomena? Have you spread out your measurements enough in space to capture the spatial scale of your phenomena? If they're remote sensing instruments, do they have a large enough spatial range that they can capture what you want to observe? Are you going to use mobile or stationary measurements? Or are you just going to set out your instruments and keep them in one place for the whole field campaign? Or are you going to move around from event to event to try to tailor your locations to the specific event you're studying? Also, what are operational constraints? You might have a region where it might be really nice to put a measurement, but it might be impractical to get there because of land ownership, because of interference from other infrastructure or other reasons. And then also, again, you want to think about how can you leverage synergies between instruments. Sometimes having two different instruments at the same location can by combining the data, you can learn a lot more, for instance. So here's a map showing how we deployed most of our instruments during wintry mix. So you see the same background terrain map that I showed you before with the operational weather stations, but now we've added all these different symbols for our different instruments that we brought into the field during wintry mix. These stars show you the locations where we were doing our radio sound launches and our manual observations. So you see we're kind of have this north-south transect, which allows us to characterize variations both along the St. Lawrence River Valley and the Champlain Valley and their confluences. You also see the locations where you have these vertically pointing radars, giving us vertical profiles to the atmosphere. These X and C symbols are the locations that we put our radars. We have our one C-band radar, which stayed stationary here, kind of giving us a good surveillance coverage of the kind of middle of our study domain. And then our two smaller X-band radars, we had them mobile, where one would move north and south up in Canada, and one would move north and south down in the US, depending on where our storms were forecast to go. So we could optimize the radar coverage for the weather as it was forecasted. And then the dash boxes that you see here, these are the different kind of general regions that we operated the Convair 580 aircraft in. So we're largely flying over these valleys, but over different sections of the valleys, down in the Champlain Valley, up in the St. Lawrence Valley, or near their confluences, depending on the specific weather forecast and our scientific goals for the day. And then again, we're thinking about these as a network, though, not just all in isolation. So when we were flying the aircraft, we're often trying to fly over some of our ground-based assets. So we would have measurements up in the atmosphere, right over the locations where we were collecting observations on the ground, or flying the aircraft along paths where the radar was scanning, so we can combine the aircraft and the radar data to do different kinds of syntheses. So here, I just want to give you a couple of examples of how some of the data came together. Here's a map showing at an individual time during one of the storms we studied, just the surface temperature measured at these different surface station networks and the near surface wind. So you see a much warmer air down here in New York and Vermont, a much colder air up here in the St. Lawrence Valley as it's coming down, funneled down the valley from the northeast, helping to maintain that cold air down in the bottom of the valley. Here's a map of the precipitation type with the different colors denoting different kinds of precipitation, for instance, rain in green and freezing rain in pink. And these are coming from all different networks, both mesoscale station networks, but also our wintry mix observers in the triangles are observing precipitation type. So we're able to map out how these variations in surface temperature related to variations in the kind of precipitation that was reaching the ground. And then here you're seeing some of the data from our radar, these colored shaded circles are showing you the scans of the radar reflectivity, allowing us to map out the precipitation structures over these valley regions that we're interested in. And the blue line is showing you where we were flying the aircraft during this storm, up and down this section of the St. Lawrence River Valley, as well as across it. And so you see this, start to see how these different data sets all layer on top of each other, and we're working out to bring them all together to understand these storms. And here's one more quick example, focusing on balloon-borne measurements. I'm showing you 3 different times from 2 different locations where we were launching radiosondes. One down in the bottom of the St. Lawrence River Valley, and one a bit to the south and the east, shown in the cyan and the darker blue colors here. And so you see in these profiles, just of temperature as a function of height, you see this very cold air near the surface, -5 to -10 degrees Celsius, but it's very, very shallow. By the time you get up to about 500 meters above the surface, you go from sub-freezing temperatures to above freezing temperatures. And these temperature profiles are very important for determining the kind of precipitation you get at the surface. A profile like this with warm air and then cold air near the surface, that can give you freezing rain or ice pellets, which are indeed what we observed. And then you also see the winds from these soundings, where you see at upper levels, the winds are coming from the south or the southwest. But at these low levels, you see that northeast flow coming down the St. Lawrence Valley, which is helping to maintain this low-level cold air. And then as we look over time, we're launching these soundings every 2 hours. You can see how that low-level cold air was maintained at this location in the bottom of the St. Lawrence River Valley, but it was eroded at this location out of the bottom of the valley, where that cold air disappeared and temperatures rapidly warmed up as the wind shifted around. And so this helps us understand how and why the precipitation phase changed as well. And so we were only able to do this, though, because we carefully thought about where we placed these observations and how often we would launch these soundings to observe such phenomena. Okay, so let's say you've come up with a good plan for a research project. You still need to find the resources to make it happen. And a big part of that is finding the financial resources. Depending on the scale and the scope of the project that you want to do, your project might cost a few $100s to put out a few cheap sensors around your university's campus, to maybe tens or even hundreds of millions of dollars. What do those expenses go to? Well, a lot of it often goes to time. People need to be paid for their work, so you need all the people that make a field campaign happen, you need to pay them. But there's also travel. You have to travel into the field. You have to ship your instruments into the field. You may need to buy instrumentation, or you may need to maintain your instruments. That can be very expensive. You have expendables. If you're launching radiosondes, you're launching these weather balloons, and then they're gone. And so every time you want to do another launch, you need to pay for another set of expendables. And there may be fees, say, to import your instruments into another country. Where do you get the money from? Well, it can vary. It could be from internal institutional funds. Like if you work for NASA, you might have access to certain internal funds, or if you work from a university, there might be internal university funds you can draw from. But a lot of the really major field campaigns, they get their funding from competitive grants to federal agencies such as NOAA, NASA, the Department of Energy, the National Science Foundation. But there can also be funding from state agencies in your local state, or even private foundations or companies. Most of these types of fundings have an application process where you have to put together a document that explains things like what you want to do, why you want to do it, the background, the motivation, your goals, your hypotheses, your research plan, your deployment plan, your budget, how much is everything going to cost, how are you going to manage the data, how are you going to analyze it after you do the field project. And so that process of writing the application is really important, and it's a really unique, special skill to have, to clearly convey all that information after you've thought it out. In addition to just getting funds to do a project, though, some agencies also have what we might call deployment pools. So these are kind of existing pieces of instrumentation that anybody can apply to use. So for instance, the National Science Foundation through NCAR has this aircraft, the C-130, that researchers can apply for time on that aircraft to go and do a field campaign, rather than having to own their own aircraft at a university, which is very rare these days. Most researchers apply to use community facilities like this to do their research, or the Department of Energy, DOE, has a mobile facility where they can deploy all these radars and different sensors into different parts of the world, and you can apply to use that facility. Here's just a listing of some of the different National Science Foundation sponsored facilities, such as aircraft facilities, surface systems, radars, airborne remote sensing systems, and so on, that any researcher, kind of any professor or research scientist in the field can apply to use these things. Okay, so in the case of Wintry Mix, we were funded primarily by the National Science Foundation through 3 grants to the University of Albany, the University of Colorado Boulder, and the University of Wyoming. The total funding was around $3.6 million between these 3 grants. And to get this funding, the main thing we had to do was write a very convincing, hopefully, 15-page grant application. So it's actually very challenging to convey all this planning and budgeting and everything and rationale in a relatively short 15 pages. And so that was something we worked for many months on doing. But also, of that $3.6 million awarded to these 3 universities, some of that was then distributed out to other entities through what were called subawards. So particularly for our 2 major facilities, the radar facility, FARM at the University of Illinois, and the National Research Council of Canada, who operates the aircraft. Large parts of those funds were then distributed to those entities to fund the use of their instrumentation. And then finally, there was many other entities that contributed time, funds, or instruments, such as researchers at McGill University and UCAM, and Environment and Climate Change Canada. Okay, so we were very fortunate. We got our project funded, and then you need to go, once you have funding, you need to go into the actual planning and execution of the field work. And so I'll kind of talk through at least some of the considerations that you need to go through when you're doing that. One important one is diversity, equity, and inclusion. It's really important to take care of all of the members in our team and make sure everybody's able to contribute to the best of their abilities. And we need to ensure, to do that, we need to ensure a safe and supportive environment for all of our team members, making sure that we're operating in a way that's equitable to everybody and inclusive of everybody. Fieldwork can present kind of unique challenges for these issues of diversity, equity, inclusion that are not, for instance, found when you're, say, working on campus or working in your office. In the field, you're often working long hours. You might be in informal settings, not like a formal office setting. There might be high stress associated with the field work, physically challenging work, and these can all lead to issues. In informal settings, people might kind of let their guard down and maybe think behavior that they would normally not deem acceptable is acceptable, and in doing so might act in a way that's harassing to somebody. Physically challenging work, you might not consider somebody's physical limitations, and you might ask of them things that are unreasonable in a fieldwork situation. So these are all things we need to kind of be cognizant of as we're planning how we're going to do our field work. One important aspect of this is just having very clear policies and expectations for how we're going to work around these challenges in order to achieve the supportive and inclusive environment that we want to have, we strive to have. Safety is very important as well. We need to make sure there's adequate rest hours for our team, so people aren't driving in challenging conditions without enough sleep and putting themselves and others at risk. Everybody knows how to safely use the equipment and follow safety standards. Everybody's traveling safely, especially if we're out studying some kind of potentially hazardous weather. And that we're also following, good health procedures. And there's many other safety things probably that I just couldn't think of at the moment. We also have to make sure we're complying with any applicable rules and laws. These could be of your research institution, of the local municipal government, the local state that you're operating in, or even the country that you're operating in. So for example, if you're launching balloon-borne observations, you need to make sure you're obeying in the US the FAA rules for uncrewed balloon flights, that you're not in violation of those. If you're traveling and trying to bring your instruments to another country, you need to deal with international import and export rules. Or if you're transmitting data from a radar, you have to follow certain rules for FCC in terms of transmission of radio signals. These are all things that we need to be aware of and compliant with. So just a few examples of how we handled some of these things in Wintry Mix. On our Wintry Mix website, we had a number of documents that we worked hard to develop and put out there as guidance to our full team. We were operating at a time when COVID was still raging pretty heavily. And so we had a lot of specific COVID safety protocols that we put forth. This included things like when we're operating in the aircraft, we had to wear our masks at all times to make sure we weren't both jeopardizing people's health, but also that we weren't jeopardizing the success of the field campaign. If we got the pilots all sick with COVID and they couldn't fly the aircraft, that would really compromise our ability to do our science. We also had a document on winter travel and operation safety guidelines to make sure people were operating outdoors in these challenging winter conditions in a safe way, and as well as a code of conduct to make sure people were acting in an inclusive way and not tolerating unacceptable, say, harassing behaviors. As part of that last effort, we actually had a training put together by Advanced Geo on improving work-based climate and making sure we were having these kind of inclusive and supportive environments. Some other things you need to consider when you're doing your field operations, how you're going to do your planning and decision making. A lot of campaigns require important decisions be made about how they're going to operate during the campaign. You don't make all your decisions ahead of time. You have to make decisions kind of on the fly. A lot of weather-focused campaigns, we have certain intensive observing periods or IOPs that we need to select certain sub-periods of our field campaign that we're really going to put out all of our effort and all of our observations to really maximize what we get from them. And then even within those, we have to make specific decisions about how we're going to operate. For instance, what time are we going to launch our balloon-borne measurements? When are we going to fly the aircraft? Along what flight tracks, at what altitudes, and at what headings? How are we going to scan our radars and LiDARs? These are all different types of decisions you might need to make, not just once, but for maybe each individual IOP that you're conducting. Often these decisions are weather dependent. So you need to have good weather information. You have to have good forecasting, good communication of those forecasts, so you can then plan your operations during the campaign. You also often want to see the data you're collecting in near real time, so you can make on-the-fly adjustments to what you're doing, or learn from one IOP to the next how to better target the types of weather that you're trying to observe. When you're making these operational decisions, you have to often balance a lot of factors. Your scientific goals. What are your questions? What are your hypotheses? How do you need to target your observations to address them? And for big projects, these goals can often be varied. There can be many different goals, and they might even be conflicting. For one IOP, you might want to operate the aircraft one way if you're trying to address one goal, and another way if you're trying to address a different goal. And so different researchers on the project might be pulling in different directions to try to get their core science questions addressed. You also got to make sure you're operating safely. You might ideally want to go out and make observations for 36 hours, but that might not be safe to ask your team members to do. So you might need to constrain your operations based on that. As well as resource limitations. You might only have so many radiosondes that you can launch. You need to be careful in how you dole them out. Or you might only have so many flight hours allocated or budgeted on your aircraft. And you might have to do this all in the face of uncertainty. We often know with the weather, we never know for sure what's going to happen. There's often uncertainty in the forecast, and you need to factor that in as you're making these decisions. So through all this, it's really important to have effective, efficient communication and collaboration between your team members. You need to be easily exchanging information, and you'd be able to work together to make these decisions as a team. So one really useful tool we had during Wintry Mix to help us in this decision making was our field catalog. This is a website put together by our colleagues at the NCAR Earth Observing Laboratory. And this was a one-stop shop that we had where we could access a lot of the information we needed for our planning and our decision making. This included real-time products from operational weather networks. We would put post our forecast briefings up onto this web page. We would have a plan of the day where we make announcements for what our plan was for our operations each day. We'd have summaries of our IOPs, reports that we could access here, and an interactive mapping tool that during an IOP, we could see where is the aircraft at any given time, what are the radars seeing, where are our sounding teams, and so on. And we also have this to look back at now now that the field campaign is over. We can go back to this website and we can replay these maps, and we can look back also at our quick look products. These are quick images of some of the observations that we collected. Another valuable thing we had on the field catalog was some tools to help us track our resources. So for instance, we had a finite amount of expendables for our radiosonde observations. So we had this nice tracking tool where for our different sounding teams, we would track how many soundings that they had used over time. And each team had about 70 allocated, so we could see, how far are we from using up all of our soundings. And so basically, if we're using them at a constant rate, we'd follow this blue line. And by the end of the project, we'd use them all up. And so we needed to make sure that we didn't overshoot too much to where we ran out of soundings before the project was over. We also had an instrument status part of our website where we could go in and we could see for all our different instruments, were they working, were they inactive, were they partially working, and that would help us plan as well. If a certain instrument was down, we knew we had to work around that in our planning process. As I said, the weather and forecasting was very important. So every day, once or twice a day during the project, we would have a forecast briefing. These were led by 2 of our PIs, but also with assistance from some of our undergraduate student forecasters. We delivered these over Zoom because our team was stationed all around different locations in Canada and the US. So we would get together on Zoom to have these briefings and discuss the forecast. And we would also leverage information from some of our different partners in this process. Communication in the field was very important. As I just mentioned, we were spread out at these various locations. So we had to use different tools for communication. We used some shared documents like Google Sheets, for instance, here to do out our scheduling, who was going to be serving in different roles and different days. We could all look at these documents to figure this out. As I mentioned, we had our meetings to discuss project planning and forecast briefings over Zoom. And then once an IOP started, we would have a lot of quick communications over Slack, not particularly to plug Slack or Zoom here. These are just the specific tools we use, but these video conferencing and team collaboration tools in general, we found I think are very useful for getting everybody together and on the same page during a field project. Okay, so finally, what happens after the field campaign? So one thing is data management. What are you going to do with all that data you collected? I'm not going to talk about the analysis part, all the science you do with it, but I will talk about some of the other data stewardship aspects. One is quality control. You need to have careful procedures that you apply to your data to make sure it's of high quality and that you flag or correct any problematic data. This can be partly manual, going through the data yourself, but also writing code and algorithms to detect any errors or issues with the data. Processing, these are things you might want to do to the data, make corrections to issues you found with it. Calculation of derived variables from the variables that you observe. You launch a sounding, you measure the temperature, the pressure, the humidity. Maybe you want to use that to calculate the convective available potential energy of the atmosphere. That's something you might do after the fact in a post-processing. Multi-sensor synthesis, where you're bringing data from different sensors together. Error analysis, conversion of your data from its native format to something that's more useful for you and other researchers to use. These are all aspects of processing that you might do after a project. Also, documentation is very important. You need to have accurate and detailed metadata, meaning data about your data, to be able to do effective research. This is things like documenting where was your instrument, what hardware were you using, what specific software were you using, how was the instrument configured, are there any known artifacts, any problems in your data, having clear units on all the data that you record. All these things are very important for having the data be used effectively after the field project. And then finally, you want to archive and publish your data. You want to put it somewhere. You went through a lot of work to collect this data. You want to put it somewhere that it can be preserved and not accidentally get deleted. And you also want to make sure it can be shared with others. You want to strive for open data that's publicly accessible and usable for other researchers to maximize its impact on the field, allowing others to build on your research, to verify your results. Fortunately, there's many tools now to allow data sets to be formally published and cited. This improves people's ability to reproduce science and also helps give data creators a proper credit. If you went through all this work to collect this data, you want to get credit when other people used it. And so having data sets that are formally published and can be cited helps give you that credit. So again, just some examples from WinTreeMix. We have this great data archive that's managed by NCAR EOL, where it's a one-stop shop where you can go and you can access all the WinTreeMix data sets. And in a couple months, they'll all be publicly available to any researcher that wants to look at them. So you can go in there. When you click on one of these data sets, you can get the data, but you can also get the documentation on the data. For instance, here's a page from the documentation for some of the aircraft data, where they're telling you where specifically on the aircraft wing each sensor was mounted, what specific make and model of the instrument was used, and so on. So all this great detail that gives you the context for the measurements that you're then going to look at. And then you can see here how there's formal citations minted for these data sets. So if you want to use this specific data set, you can cite it in a paper and give the data set authors credit. And there's this nice digital object identifier, or DOI, that aids in that citation. And you can click on it and it brings you directly to the data. And then finally, communication is really important. You go through all this work to collect this data, to be a good steward of the data, but it's only really useful if others can learn from it, right? So there's a whole host of different audiences you might want to share your data with. Often we're thinking about sharing it with other scientists. We're often doing that by publishing scientific papers, by presenting our data, our research results at conferences. But it's also important to share with other types of users as well. Stakeholders, if you're doing weather research, you might want to share what you learn with forecasters so they can better forecast the phenomena you're studying, or maybe resource managers. If you're studying rainstorms, maybe you want to share that information with people that manage reservoirs so they can better manage those water resources, or even private sector companies. Policymakers, if you're doing research that's policy relevant, you want to have maybe lawmakers learn about your research so they can use it to inform policy. Your research can also have benefit for education, for students, and all the way down from K through 12 up through college and graduate students, and even for the general public. It's great to use your skills as a scientist to share your love of science and your knowledge with just general people in the society. So a few examples of how we did this in WinTreeMix. Here's an example of one of our undergraduate students presenting a poster at a local conference in about a week. I'll be presenting some of our research at the AMS annual meeting. Here's another regional workshop that we did, which is more focused on forecasting, where we had some presentations. So this is kind of getting towards those stakeholders, those forecasters. But then we also had communication geared towards the general public. We worked with journalists who published online news articles about our project, online and TV video segments about it. We had an open house at our university where media and students came by to learn about the sounding observations and the radar observations we were collecting. And then we also used social media to share what we were doing through a WinTreeMix Twitter page. Okay, so that was a lot, but hopefully you get a big broad brush sense of kind of what goes into planning and executing a field campaign, and through the lens of this WinTreeMix campaign that we just completed. So hopefully you come away from this, seeing that these atmospheric science field campaigns are a rewarding and vital part of our science, and that they're not just about going into the field and collecting the data, although that's obviously the core of it. There's all these things that happen before the campaign: identifying your research problem, planning things out, securing resources, all the details of how you do those field observations, and then the things that happen after the campaign, carefully managing your data, all the analysis that you do on the data, which we didn't even talk about today, and then communicating your science to others. So for all of us to be successful, we need collaborative and diverse teams that have varied skills to work together. You see the whole range of skills, everything from technical skills of operating instruments to writing skills for communication to logistical skills for planning and teamwork skills. You need it all to pull it off. And so, no one person can do these campaigns alone. We need to really bring together these diverse teams and work together effectively to do so. So thanks for your time. I hope you learned a lot, and I encourage you to check out some of these links that I've included in the presentation if you want to learn more about the Wintry Mix field campaign. Thanks.